Hello everyone, I am Dr. Jayakishan Noja, Assistant Professor of Physics from Government Degree College, Lakshadweep. So in the series of lectures on statistical mechanics, this is my fifth lecture, and as you have seen in the last lectures, uh, we had right from the introduction of statistical mechanics, then about the microstates, macrostates, then symbols. Yeah, then we had the method of statistical mechanics, that is your classical statistics and quantum statistics. Then we had a discussion about the probability theorems, some examples on the probability theorems. And then we had the classical statistics. So under the classical statistics, we know it's applicable to the molecules of a gas, and we had used the Maxwell-Boltzmann distribution there. As you know already, we derived the Maxwell-Boltzmann distribution in the kinetic theory of gases. So the same equation here we derive using the statistical mechanics based upon the properties of the molecules. For the whether the system is following the classical or quantum. So if it's following the classical statistics, we get the Maxwell-Boltzmann distribution. So we have seen the distribution of particles in different energies. Then we had calculated a formula for the average energy of the molecule. Yes, then of the ideal gas. Then we had the distribution of molecular velocities. Yes, so this all was done in the lecture 4. So now proceeding to lecture 5. So here today we will see the quantum distribution. Okay, so we know in the quantum distribution of quantum statistics, first we have the Bose-Einstein statistics. So first we need to derive the distribution law. Why? Because whenever you want to uh, apply this Bose-Einstein statistics or any statistics, you should know the distribution law. Okay, then based upon the particular distribution law, we have to apply the particular distribution law in the general formula. Then we can go for the applications. So we know this Bose-Einstein statistics is applicable to those particles which are identical, indistinguishable, and which have integral spins. Yeah, the spins of these particles can be either 0, 1, 2, and so on. And remember that the wave functions of these particles, it overlaps. Yes. So such particles are known as bosons. So I was saying we have a number of examples. So most popular are photons and alpha particles. Yes. So now you see what is the distribution function. Yes, so distribution function is nothing but it gives the probability of distribution or probability of the particles occupying the given energy states. So here the probability function f is, which is a function of energy, that a boson occupies a state of energy E is given by f of E is nothing but 1 by E. In the power we have alpha plus E by kt. So we have to remember that this alpha is a constant and it is a function of the property of the system as well as temperature. And then we have k we know it's Boltzmann constant, and T we know it's the absolute temperature. So this equation 1 is known as Bose-Einstein distribution function. Yes, why? Because it is applicable to the particles which are obeying the Bose-Einstein statistics. Then the actual number Ni of particles with energy Ei is given by, we know this formula, yes, N of E is equal to G of E into F of E. Here we are putting Ni where I is the number of particles. Yeah, it can range from 1 to infinity. Yes, so this is nothing but Gi. You are putting the value of F of E here. So you'll be getting Gi by E to power of again alpha plus Ei by kt minus 1. Now, what is G of E? We know G of E is nothing but is the statistical weight. So, it gives the number of quantum states available for the particles of same energy E. Yes, this is known as your Bose-Einstein distribution law. So, when the energy distribution is continuous, what we do? We will replace your or we will add dE. Yes, so the number of particles which are having the energies lying between E and E plus dE is nothing but given as NIE dE is equal to GI of GI into dE by again the same thing E to power of alpha plus ei by kt minus 1. Yes. So this is your Bose-Einstein distribution law. Now you see, so whenever we uh, do something, yeah, we have to first go for the applications. Why? Because everything in the physics has some applications. Yes. So here, what is the use of deriving this law? So using this law, you can calculate the your well-known popular Planck's radiation law. So here we will apply this Bose-Einstein distribution to photons. Yes. So on the basis of quantum theory of radiation, we know Planck proposed that energy is emitted in the form of photons, and each photon has the energy h nu, where h is nothing but your Planck's constant, and nu is nothing but the frequency of radiation. Yes, why? Because we know, again, if you take the radiations, means yeah, it's sunlight or anything. Yeah, it consists of photons. So again, we know, already we have studied this in your black body radiation or quantum theory of radiation, that the black body radiator contains simple harmonic oscillator of all possible frequencies. Yes. Again, we are saying it's having all possible frequencies, but it's not continuous. Yes. The oscillator cannot emit or absorb energy continuously. The emission or absorption of energy takes place in discrete amounts, that is, the energy is quantized. So we have to remember that you have something like energy packets. Yes. So that is nothing but quantum of radiation. Yes. So the energy is quantized. This is very important thing. Why? Because we have to remember that the simple harmonic oscillator may have all possible frequencies, but it is not continuous. Yes, it can emit or absorb energy only in some packets. Okay, quantized. It's quantized. So we have something energy packets. So we say that the energy of the harmonic oscillator of the frequency nu can have only certain values like 0, h nu, 2 h nu, and so on. So we have learned much about your radiations in the previous chapter. That also you can add here. Yes, something like that. Like if you take the spectrum of this black body radiation, what happens? The spectrum is it's a full frequency range you have there, but we have to remember that it also depends upon temperature. Okay, so what happens when we raise the temperature of this material or black body? What happens? Your there is a shift in the wavelength. Yes, so we know the wavelength of maximum intensity shifts towards the shorter side. Yes. So if you as you are going on increasing the temperature, the maximum intensity shifts towards the shorter wavelength. Yes, we have something lambda suffix m into t is nothing but constant. It's the Wien's law. Yes. So we have some small observation. So that what happens when you are heating the black body, the color goes on changing continuously with temperature. Yes. So it signifies, yeah, it signifies that do you have something relation between the temperature and the wavelength. Yes. As the temperature is increasing, definitely the wavelength of the emitted radiation also changes. Yes. So all this you can put here. Um, again we know the average energy of the oscillator is nothing but it is given as h nu by e to power of h nu by kt minus 1. That is your average energy of the oscillator is nothing but the total energy. There what we do, there we take the total energy divided by the number of oscillators. So we write E by N, where capital E is the total energy and capital N is the total number of particles or total number of harmonic oscillators, yeah, which are continuously emitting and absorbing radiation. So we know this according to Planck's the energy distribution of photon gas is given by E of nu is nothing but 8 pi h nu cube by c cube into 1 by e to power of h nu by kt minus 1. This is your popular formula. You have to derive this formula using our hypothesis or our Bose-Einstein distribution law. So what we do, we need a black body. So we have to create a black body. You take a opaque material and you make a cavity. Yeah, you make a cavity in it. Yeah, we know what is the cavity. Yes, cavity is nothing but it's the empty space. Yes, you have to create some empty space in the material, and as we demonstrate in the previous chapters of black body, yeah, you have to make the radiation fall on this black body. So the black body, what it does, you have the continuous reflection of the radiations inside the black body. So you have a continuous emission and absorption of radiation in the black body. So here, suppose we imagine that the volume of the cavity is V, and it contains a large number of indistinguishable photons of various frequencies. Yeah, we call this as photon gas. Why? Because you are having a large number of photons. So photons are nothing but bosons, and they obey the Bose-Einstein distribution law. So accordingly, what we have to do, we have to use the your Bose-Einstein distribution law here. So this we have already given in the previous title, that you have to put here. So in case of cavity, that is the empty space of the opaque material, the number of photons is not fixed. Why? Because you are having the absorption and emission by the walls of the cavity. Yes. So if sometimes it may happen that 10 photons are absorbed and some 8 photons are re-emitted. Yes. So always your absorption and emission will be different. Yes. So you will not be having the fixed number of photons. So we can say that the number of photons is not constant. Yeah, or it is not conserved. So this will lead to your alpha equal to 0. Why? Because we were saying that alpha is a constant which depends upon the property of the material and temperature. Yes. So your law is simplified. Why? Because you are putting alpha is equal to 0. So your Bose-Einstein distribution law now becomes Ni is equal to Gi by e to power of, yeah, e is nothing but exponential. Yes, exponential to power of Ei by kT. Yes, where Ei is now energy, and again the same your constants, K is nothing but Boltzmann constant, T is your absolute temperature. Yes. And again what happens is, why? Because we are having a number of photons in a small cavity. The energy difference between the successive values is very small, means all the photons will have the energies in a close range. Yes. So what you can do is you can replace Gi by G of E dE and your Ni by Dn. Yes. So in place of Ni, you will be writing Dn, which is nothing but G of E dE, again exponential E by kt minus 1. So here we know we are dealing with the frequencies here. Why? Because in your back body radiation, we deal with the wavelengths, frequency, and all these things. So here, so what we do is we will convert this energy into your frequencies. So we know E is nothing but equal to h nu. Yes. So uh, you'll be writing all this thing in terms of nu. So G of E d is again written in the form of G of nu d nu. So the number of states in black body radiation in the frequency range nu and nu plus d nu is given by, again the same formula. Here we will be putting nu. So G of nu d nu is nothing but 8 pi by c cube into capital V nu square d nu. So you have to remember that this V is nothing but it's a volume of the cavity. Yes, where you are having the photon gas. Then nu is nothing but it's a frequency of the radiation. Yes. So you see these are nothing but the energy states. Yeah, it's a statistical weight. Why? Because you see whenever you have a distribution, um, you should know the number of available states. So in these states you will be arranging the particles. Yes. uh, Likewise in your Maxwell Boltzmann distribution, there what we do is we will take the momentum space we are taking there. In the momentum space, again we have taken a sphere. Yeah, sphere of some radiation radius p and thickness dp. So there, that space is nothing but it's a statistical weight, means that is the space available for the molecules of the gas. So here what we do is we are taking the frequency range. So the number of states of the in the black body radiation in the frequency range nu and nu plus d nu is nothing but this one. So we need to remember this formula. Okay. Again, if you want, you can derive this also, but it's a time consuming. So here we need to remember these values. So this is nothing but the statistical weight. So in your equation 4, you have to substitute this. So if you substitute this, you are getting the equation something like the equation 6. Again, what we do is we will take dn by d nu. Okay, so dn is nothing but the total number of particles, and d nu is nothing but the frequency range. So if you consider dn photons in the frequency range nu and nu plus d nu, the energy will be h nu into dn. Why? Because dn is the total number of particles or photons, yes, in the frequency range, and h nu is the frequency, sorry, energy of each photon. So the energy of each photon multiplied with the number of photons in that range will give you the energy. So the energy per unit volume in the frequency range is nothing but, if you divide this h nu d, and that is the total energy with volume, you will get the energy per unit volume or density of the radiation. So therefore the energy distribution for photon gas is given by E of nu. D nu is nothing but h nu by V into dn. Yes. So we need to remember that one thing is the energy is nothing but your number of photons into energy of each photon. Yes, always the energy of each photon is quantized and it is h nu. So if you multiply h nu with dn, you will get the energy, and if you divide this with volume, you will get the energy per unit volume. So substituting these values from equation 4 in equation 5, you will get E nu is equal to something like this. Or if you simplify this equation, you will be getting E of nu is nothing but 8 pi h nu cube by c cube into 1 by exponential h nu by kt minus 1. So this is your very popular formula. It is well known, Planck's radiation law. It gives the energy distribution of a photon gas. So we are deriving this law using our statistical mechanics. So uh, yeah, we have already seen this equation. Yeah, this equation was there in the quantum theory of radiation. The same equation we are deriving here.